This is our first lesson on momentum and impulse. And to start with, I'm going to tell you that when Newton described his second Newton's law, he didn't write it as F equals to ma. He didn't say F is equal to ma. He wrote it this way. He wrote that if you apply a force over some time, this is going to be called impulse. So force applied on an object over time is going to be called impulse, and it has a letter J. Then the momentum of the mass will change. So mass times change of the velocity is the momentum. So this is impulse, and this is momentum. So the impulse is equal to the change of the momentum. So let's say you apply, let me give you this example. If you are on the skateboard and you are heading toward the wall, you can keep your hands to yourself and hit the wall as it is without using your hands to prevent getting hurt. So what you're going to experience is this. You're going to experience big force over small amount of time to change your mass, change of the velocity. So you have a mass, you have some initial velocity, final velocity is going to be 0. So the change of the velocity is going to be some number in the mass that you have. Or you could do little force if you put your hands in front of you and stop yourself over bigger or larger amount of time. So it still will give you the same change of the momentum. So the momentum is going to be mass times velocity. Change of the momentum, delta P, is mass times change of the velocity. And force times the time is going to be called impulse. Impulse is measured in newtons times seconds. And momentum is measured in kilogram meters per second. But they're exchangeable, so you can say impulse is in kilogram meters per second and momentum is newtons times seconds. So it doesn't matter which one you choose to write your units when you solve problems. But this is one of the main formulas that you need to know in this section. Another important formula to know in this section is conservation of momentum formula. So there are different types of collisions, and I'll go over it as soon as we get to the collisions, but there are different types of collisions. So you can have a ball is hitting another ball. So let's say one ball is moving this way, the other ball is moving this way. In this case, if they say in opposite direction, the one is moving south, the other one is north, and one is moving east, the other one is west. So in this case, you have to say, so this is initial velocity of the first one, this is initial velocity of the second one. In this case, you have to make sure that one of them is negative, and you choose which direction you want to be positive and which one is negative. So this is mass 1, this is mass 2, and so there are different ways they could collide. One of the collision, they could hit each other and then bounce back. After the collision, the first one may have some new velocity final one, and the second one can have new velocity final 2. One of them is probably going to be negative because it changed the direction. In this case, we're going to call this collision where you had two objects and you still have two objects after collision. We're going to call it elastic collision only if the energy conserved. What does it mean, energy conserved? Your kinetic energy here, initial, is of the system is equal to 1/2 the mass 1 and the initial 1 plus 1/2 mass 2 v initial 2 squared. And it doesn't matter that the other one is negative v2 because it squares and it gives you positive. So, and then after the collision, you have kinetic energy final is equal to 1/2 mass 1 v final 1 squared plus 1/2 m2 v final 2 squared. So if, only if, your initial kinetic energy is equal to the final kinetic energy after the collision, then this collision is going to be called elastic collision. And in elastic collision, in elastic collision, we have a special formula. What we say, conservation momentum also happens. Actually, conservation of momentum always happens. Energy is not always conserved. So what does it mean, conservation of momentum? So for conservation of momentum, I'm going to write momentum before is equal to momentum after. So what is my momentum before? So this is my before, and this is my after. For my before, I have initial velocity, or mass 1, initial velocity of the first one, plus mass 2, initial velocity of the second one. And you have to make sure you plug in the second one in the negative number, because it moves in the opposite direction. Usually I don't tell you you have to be cautious about negative numbers, but in momentum you have to be very cautious. So the momentum we said is the mass times the velocity. So you say momentum of the first one plus momentum of the second one before the collision equals to, that means it's conserved, equals to momentum of each afterwards. So you would say mass 1 velocity final 1, not squared, plus mass 2 velocity final 2. So this is what means conservation of momentum. The momentum of both before is equal to the momentum of both after, and this is what this formula means. So this is for elastic collision. Again, elastic collision only when energy is conserved. Sometimes they will give you on AP exam a question, and they will say the collision happened, calculate velocity of one of them after the collision, and then they will ask you, is the collision elastic or inelastic? And this is what you have to do to figure out if it is elastic or inelastic. You have to change check kinetic energy before and kinetic energy after. And for inelastic collision, so here you had, it's not 100% exact way to look at it, but it's one of the ways to look at it. So for elastic, I always think about elastic. You stretch it and it always goes back to the original shape. So for elastic collision, you have two objects and you still have two objects after. So you had two objects, you have two objects after, they just move in opposite direction. It says you only can say that it is elastic collision if energy is conserved. So you have to check it, but one of the ways to remember which formula to use is that you have two objects before, you have two objects after. For inelastic collision, there's two types of inelastic collision. One of the inelastic collisions can be you have a block, and let's say you have a bullet. The bullet gets into the block, passes through the block, and continues going. It is with some velocity. So let's say there is initial velocity, there is final velocity, and the block has some velocity as well. Maybe it wasn't moving before. So what you have here is momentum is still conserved, but in this case, not all energy is going to be conserved. So if energy is not conserved, it is inelastic collision. And you can see that part of the energy was used to rip off through the block. And because the block is damaged and the bullets is probably a little bit damaged as well, some of the energy was taken away to do this damage. So energy is not conserved. So this one is called elastic collision. And perfectly inelastic collision, let's say you have one ball, maybe it's a snowball, and another snowball. So before, the one is maybe moving, the other one is not moving. So then one is hitting the other one. And then after the collision, maybe you have one, and then the other one is stuck to it, and they move with the same velocity. So you could use the first formula for inelastic collision, because you had the bullet, and you had the block, and you have the bullet, and you have a block after the collision. So the first formula is still going to work. Or if it's perfectly inelastic collision, when the first ball is stuck now to the second one and they're both moving with velocity, you would use the second formula. And in this formula, you see this. You have momentum maybe of the bullet and momentum of the block. And afterwards, they both stuck together and moving with one velocity. So this is the types of the collisions, elastic and inelastic collision, and conservation of momentum, and what impulse equals to, and what it means in momentum. And now we're going to look at some of the questions and how to use what I just explained to you. Also, there's something important to know about momentum and impulse. Every time there's going to be a collision, like I already said so many times, collision within 10 minutes that I have this video. So every time there's a collision, there's most likely that you have to use momentum in solving the question. So you would use conservation of energy to check if it's elastic, inelastic collision, and you would use conservation of momentum, which always works. So here's our first question. An SUV with a mass of 1,800 kilograms is traveling eastbound at 15 meters per second, while a compact car traveling with a mass of 900 kilograms is traveling westbound at negative 15 meters per second. Usually they will not tell you it's negative, but because one is moving one direction and the other one is moving the other direction, here they place negative. Usually they will not tell you, but you have to place negative. The cars collide head-on, becoming entangled. So it is perfectly inelastic collision, or I will say inelastic collision. Find the speed of the entangled cars after the collision, find the change of the velocity of each car, and then find the change in the kinetic energy of the system. So I'm going to start with the conservation of momentum. The conservation of momentum says momentum before is equal to momentum after. For momentum before, I have 18 kilogram car, momentum before, moving at 15 meters per second, mass times velocity is momentum, plus momentum of the second car, it's 900 kilogram car, moving at negative 15 meters per second, and then afterwards they stuck together, so their mass together is 2,700 kilogram, and times their final velocity. So from here, what I did is this: mass 1 times velocity 1 initial plus mass 2 velocity 2 initial is equal to mass 1 plus m2, they stuck together, moving at some final velocity. So now I see that I can divide all three of them by 3. So I divided the first term by 3, the second term by 3, and the third term by 3. Then I'm going to divide all of them by 100 as well. I could divide them originally by 9, so I'm going to divide them one more time by 3. Actually, I can divide by 9. I'm going to divide every single one of them by 9. So I divide this one by 3 and by 3. So I have 3 and 5, 2 and 5. I divide this one by 3 and by 3, which I'm divided by 9. So that gives me 5. And I divide this one by 9. So it gives me final velocity. So the final velocity is equal to 5 meters per second. So that's the answer for the first question. If the speed of, what is the speed of the entangled cars together? So that is 5 meters per second. And I got a positive 5, so that means they're moving eastbound. So they're stuck together and they're moving eastbound. Then I have to find the change of the velocity. So this was my A part. Now I'm going to do B part. I have to find the change of the velocity for each car. So the change of the velocity of the first car is the final velocity minus the initial velocity. So that gives you negative 10 meters per second. So the first car lost 10 meters per second in velocity. And the change of the velocity for the second car is 5 minus negative 15. And that gives me 20 meters per second. So the second car lost, or its velocity changed by 20 meters per second because it was moving 15 meters per second in one direction, but now it moves 5 meters per second in the opposite direction. So the second car experienced more acceleration because over the same time, the change of the velocity of the second car was bigger. And for the last part, I have to find the change of the kinetic energy of the system. So I'm going to do kinetic energy initial was equal to 1/2 mass of the first one, velocity initial of the first one squared, plus 1/2 mass of the second one, velocity initial of the second one squared. And I got 101,250 joules. And I noticed that both of them had, so the mass was 1,800 and was 900. So I took 900 out. So what's left is only 2 and 1. and then both of them had 15 and 15 velocity before squared. It doesn't matter whether one was negative, so I took 15 squared out, and both of them had 1/2, so I took 1/2 out of the parenthesis, and then I calculated my initial kinetic energy. For the final kinetic energy, I have them both stuck together, so I have 1/2, and their masses stuck together, so that's 2700, and then their velocity is 5 squared, so that gives me 33,750, so 33,750 joules. And the change of the kinetic energy, you see that energy is not conserved, because energy before is larger than energy after, and the energy that is lost probably to the sound, to the heating up the parts during the collision, to the damage done through the collision, maybe through the friction. So energy lost in different types of energies, and so the change of the kinetic energy is equal to the difference between these two, the loss of the kinetic energy. So that gives me negative 67,500 joules. So that's how much energy was lost during the collision. So that only tells you that because energy is not conserved, you know for sure that collision was inelastic. And one of the ways I remember inelastic, one object gets into another object by damaging the other object. So inelastic, there's some damage done, energy is not conserved, and one gets into or through the other one. And elastic, you had two objects before, you have two objects after, no damage is done. Same shape, same energy as before. Here's another question. A golf ball with a mass of 50 gram. 50 gram, let me convert it with you. So 50 gram, that's the same as 50. If I place kilo, I make it 1,000 times bigger. So I need to make -3 to cancel kilo. So that gives me 0.05 kilogram. So a golf ball with a mass of 0.05 kilogram is struck with a club as it is shown in the figure. The force on the ball varies from 0 when contact is made up to some maximum value when the ball is maximally deformed, and then back to 0 when the ball leaves the club. Assume that the ball leaves the club face with a velocity of 44 meters per second. Find the magnitude of the impulse due to collision and estimate the duration of the collision and the average force acting on the ball if the force acted on the ball over the distance of 2 centimeters. So let's underline everything that is given. So here I have 2 centimeters and I have 44 meters per second after the collision. I have the mass of the ball, and I believe that's all that is given. So if I look for impulse, the impulse formula is force times the time is equal to mass change of the velocity. Well, it's the same formula as force is equal to the mass change of the velocity over the time, mass times acceleration. They don't give me the force and they don't give me the time, so I can find my impulse. So this is my impulse is equal to the mass, which is 0.05 kilogram. Change of the velocity. The final velocity is 44 and the initial velocity was 0. So that will give me 2.2 and measured in newtons times seconds. So that is newtons seconds. And then estimate the duration of the collision if it happened over the distance of 2 centimeters. So I know that the distance is equal to average velocity times the time. And the time is equal to the distance over the average velocity. The distance is 2 centimeters. Centi means 10 to the negative 2. So I have to move the decimal 2 positions back. And then average velocity, initial was 0 and the final is 44, so that is 22. So that gives me 0.01 divided by 11. And I get the number which is 0.0009, so I get 0.0009 seconds, or 0.9 milliseconds. So I got the time. and then I can plug it in into my impulse formula to find the force. So the force is equal to the mass, 0.05, change of the velocity, or actually I already know what this number is, right? So I'm just gonna plug it in. So I just figure out what that number is equal to, and then I will divide by the time to find out. So I already know what this is equal to. Divide by the time. So I have 2.2 divided by the time, which is 0.0009, and that will give me 2,444.4 newtons. So this is the force that was applied on the club to change its velocity on the club, or by Newton's third law, the club applies exactly the same force as the ball applies on the club. So this is the force that the ball applied on the club, and the club applied on the ball and changed momentum of the ball. Here's another example. In a crash test, a car of mass, I'm going to underline as I read, 1,500 kilogram collides with the wall and rebalances as shown. The initial and final velocity of the car are negative 15 and then positive 2.6 meters respectively. So before it was negative 15 and after it was 2.6 meters per second, change the direction. If the collision lasts 0.15 seconds, find, and I have to find the impulse, and I find the size and the direction of the average velocity exerted on the car. So to calculate the impulse, again, I'm going to write the formula. Force times the time is equals to mass change of the velocity, and plug in my numbers. So the impulse is equal to the mass, which is 1,500 kilogram, times change of the velocity. The final velocity is 2.6 to the right, and minus initial velocity, negative 15 to the left. And so the impulse is equal to 26.4 kilo, which means 1,000 newtons times seconds. And then for the second part, they ask you to find the force. So if I know the force times the time is equal to 26, that's not right, kilo, we're going to say 26,400 newton seconds, and the time was 0.15 seconds. I don't have to write the seconds here. Then n equals to 26,400. Then the force is equal to 176 kilonewtons. So this is the end of our first momentum video, and check for descriptions. You will see the link to the next video for momentum 2.